Okay, today we've talked before about heat and a heating curve, but today we're going to put equations on the heating curve, heat equations on the heating curve. There are different equations on different parts of the heating curve. Okay? Now, when you have a solid, when a solid is occurring, you will have a temperature change. A temperature change. So what we're going to do is we're going to take these equations, okay, on the margins here, and put them where they belong. If you're heating a solid, let's say for example ice, then you have a temperature change. Then, in order to find the amount of heat energy you need, you would move this equation over here, and you would use Q equals MC T2 minus T1. Now remember, when we talked about T2, we were always going to T2 because that's the final temperature. As you add heat and you move up the curve, you begin to melt the substance. Notice when you begin to melt the substance, the temperature does not change. Okay? It does not change. Now we've demoed that before in class when we melted ice with salt and the temperature stayed at -4, -8 degrees. It didn't change. When you melt ice, all the energy goes into breaking bonds and the temperature stays where it is. So we can't use a temperature change here. There is no temperature change. So instead of using a temperature change, we're going to use Q equals delta H, or excuse me, fusion. And it's not fusion like a nuclear bomb. It's fusion before fusion was invented. So fusion in this case is describing melting. And you multiply it by the number of moles of substances you have. You could also use the delta fusion and mass. It really just depends on whether you get moles or mass in your delta H of fusion. You will not be required to memorize this, okay? It's good if you do, but this right here will be given to you. That'll be usually given to you in a problem. Okay, your job will be to calculate Q. Moving on, up the curve. When you enter the liquid phase after everything's melted, do you have a temperature change? Yes, because this curve is going up. So what equation would we use during the liquid phase? That's correct. We would use Q equals MC T2 minus T1. Okay? You can only use that during the liquid phase. Then as we add more heat, what begins to happen? It begins to vaporize. It begins to vaporize. Boiling. Boiling occurs here. This is flat. There's no change. The temperature is not changing. Not changing on this graph. So we can't use Q equals MC T2 minus T1. Instead, we're going to use Q equals moles of vaporization, or we can use Q equals mass delta H vaporization. And again, you're not going to be required to memorize anything here. You'll be given delta H vaporization in a problem. Okay? So I wouldn't worry too much about memorization. Your job will be to calculate Q. In the next video, we're going to go over how to cancel units, because that's one of the most important skills you can learn. And finally, in the gas phase, we have a temperature change again, and we can go back to using Q equals MC T2 minus T1. So, the bottom line is, folks, on the slope part of the graphs, where you have temperature changes, you can use Q equals MC T2 minus T1. See, there it is, solid, liquid, gas. Parts of the curve. Anytime you have a temperature change, you can use Q equals MC delta T. The letter C, remember, the letter C is specific heat. It's going to be different in different phases, and it will usually be given to you in a chart. But when you get to the flat parts, here, you don't have a temperature change, so you need to use Q equals mass times delta H of fusion, or moles delta H of fusion. Okay, and then when you're boiling or vaporizing, we use mass times delta H of vaporization, or Mole's delta H vaporization. So how do you know when to do it? Temperature change or not a temperature change. Temperature change or not. And that is how you solve for all of the letter Q's. Q's meaning heat. Okay?